Good afternoon. In this video, I will be presenting my digital assignment 3 based on the implementation of NAN to Tetris project from 4 to 6. These projects focus on hack assembly programming, complete computer architecture design, and assembler development. The objective of this assignment was to understand low-level programming and hardware-software interaction within a computer system. Specifically, the assignment involved implementing machine-level programs using hack assembly, designing the hack computer architecture, and developing an assembler to convert assembly instructions into machine code. Project 4 focuses on machine language programming using hack assembly language. It introduces direct low-level instruction programming and helps us understand how the processor executes operations without high-level abstraction. The two tasks completed in this project were mult- mult.asm and fill.asm. The first task was implementing multiplication using hack assembly language. Since the hack platform does not provide a direct multiplication instruction, multiplication was implemented using repeated addition, and the program takes input values from the registers R0 and R1, repeatedly adds the first number based on the second number of iterations, and stores the final result in register R2. As shown in the output, when values 3 and 4 are provided, the result generated in R2 is R int 12. The second task in project 4 was fill.asm. This program continuously monitors keyboard input through the keyboard memory register. If a key is pressed, the screen memory is filled with black pixels. If no key is pressed, the screen is cleared to white. This demonstrates memory mapped input and output handling within the hack architecture. Project 5 focuses on constructing the hack computer architecture. In this project, separate hardware modules are integrated together to build the complete working computer. The major components implemented include the memory chip, the CPU chip, and the final computer chip. The memory chip is responsible for routing memory access between RAM, screen, and keyboard. Based on the provider address, the chip determines which hardware memory component should be accessed. This also enables memory mapped input and output, where devices like the keyboard and the screen are treated as memory locations. The CPU acts as the central processing unit of the hack computer. It decodes instructions, performs arithmetic and logical operations using the ALU, updates the register, and controls the memory write operations. Additionally, it uses ALU output flag to determine jump conditions and update the program counters accordingly. The computer chip integrates the CPU, memory, and ROM components into one complete architecture. It enables the hack computer to fetch instructions from ROM, process them using the CPU, and interact with memory components during execution. Successful test outputs confirm the proper working of the complete integrated computer system. Project 6 involves developing an assembler in Python. The assembler converts hack assembly language instructions into binary machine code that can be directly executed by the hack computer. This establishes the connection between human readable assembly instruction and machine level binary execution. The assembler follows a two-pass translation approach. In this first pass, labels are identified and stored in a simple table along with their corresponding row matrices. In the second pass, the assembler processes each instruction, resolves symbols and variables, and converts assembly instructions into 16-bit binary machine code. As demonstrated here, the assembler reads the input assembly file, processes each hack instruction, and generates equivalent machine code in the output hack file. This confirms successful conversion of assembly instructions into binary format. In conclusion, through Nanto Tetris Project 4 to 6, I successfully implemented machine level programs, built the hack computer architecture, and developed an assembler in Python. These projects involve practical understanding of instruction execution, processor design, memory management, and software hardware integration. Thank you.